So I have here a very special stone given to me by my old friend Nicholas Flamel. And this stone, in fact, it's the only one of its kind. It's known as the Philosopher's Stone, and I'm quite precious about it. I don't let most people look at it. I keep it hidden upstairs. And you may ask, how do I know if this is a genuine article? Is this real or is this a fake? Have I been given a duplicate? Well, it's the same when we look at any kind of stone, really. They're high value of things like jewels, diamonds, sapphires, rubies, emeralds, such like. How do we know if we have a real one or we have just a piece of glass that has been created and shaped and coloured to look the right thing? Well, of course, what we can do is we can check out the colour of it. Does it look the right colour to be what it is claimed to be? Is it as hard as we expect? Can you scratch it? I mean, diamond, for example, is the hardest known substance, so no other material can scratch it, but it can scratch other materials. But actually, what scientists do is they shine light through it. By shining light through it, you can test to see if it is the real thing. You see, for diamonds, sapphires, emeralds, rubies, and the Philosopher's Stone, there is an amount of refraction that we would expect based on the material properties of this stone. Certain stones slow down light much more than other stones, and so they refract light much more than other materials. Every material has its own amount of refraction that we would expect, and we call that the refractive index. Now here, with this stone, you can see, if I hold it in front of the camera here, as I shine the laser beam in, it goes straight through the stone. As I shine it in an ever-increasing angle, that what you can see is the ray of light is basically bending and is now coming out. Can you see that? The ray of light is going through a very funny angle. This would have a very large refractive index, which, to my mind, makes me think that this is the real thing. So how about it then? Let's talk about this thing that we call the refractive index. Sounds complicated, doesn't it? But all it is the amount of refraction that we would expect to see in a material like this one. That's all it tells us. Materials that refract a lot have a high refractive index. Materials that don't refract a lot have a low refractive index. But I want to explain to you where this number comes from and exactly what it means. Well, first of all, the symbol that we use for refractive index is the symbol lowercase n. And n normally tends to be quite a small number. It's never less than 1, but it's never normally more than about 3. And so the number is quite small. An interesting fact about the refractive index is it has no unit. It's amazing. It's one of the only quantities in physics that is unitless. The physics teacher may be forever telling you, shouting at you and saying you must include your units. Well, here is a genuine quantity that has no unit, for it simply is a ratio of two quantities that you could measure. Now, those two quantities are as follows: C and V. And the refractive index of a substance, anything that is transparent can have a refractive index. Glass, water, perspex, or diamonds, or salt water, or the Philosopher's Stone, any such thing. Well, it is the speed of light in a vacuum. So that is that top speed, discovered a very long time ago, divided by the speed of light in that substance, which is unique to that material. Some materials really slow it down, and some materials don't. So let's have a go at some numbers, shall we? Well, I have my calculator here, because this is the sort of job which you'll need a calculator for. For water, let's talk about water. With water, the speed of light in water water is equal to, and I wrote this down because it's not the sort of number that I keep in my head, 225 million. 56,264 meters per second. Look at that. That's quite fast. But the speed of light in a vacuum is faster. So we can work out the refractive index of water. Refractive index of water is equal to the speed of light in a vacuum, 3 times 10 to the 8, 300 million, 3 followed by 8 zeros, divided by this number here, the 225,056,264. This is going to tell me the refractive index of water, 3 times 10 to the 8, divided by 225,056,264. And the answer is 1.333 with no unit. Now, I want you to imagine a different substance now. A different substance just to compare how it goes. I want to know the refractive index of diamond. So it starts out 3 times 10 to the 8 divided by, and the speed of light in a diamond is 120,810 meters per second. So if we do this sum, 3 times 10 to the 8 divided by 124,120,810, and we get that the refractive index of diamond is 2.417. And so you can see the number for diamond was higher because it slowed down light more. And so therefore, in diamond, we would expect to see more refraction, more bending of the light than we would in water. First things first, I'm going to draw around this square or rectangular piece of perspex here. That's so that if I move it, I can put it back again exactly where it originally was. It's surprising how many people don't do this and then end up really stuck. The next thing I need to do is I need to draw a normal line onto this where I intend the laser beam to go into. So if I mark a point there, I'm going to use my protractor here to very accurately draw a normal line, because I'm going to get a better answer if I'm more accurate. It is coming out there, which means that my normal line goes straight through my material like this. That is at 90 degrees to the boundary between the air and the glass block. So I'm now going to put my glass block back on here. And what I'm going to do is I'm going to send my light into the glass block at an angle. Doesn't really matter which angle, but I'm going to use this one. And how I mark it out is I put a little X here, and then a little X here, and then I'm going to put a tiny little X just here, where it is coming out of the other side. You see, when I take that away, and just shift that down off the laser line, it enables me to draw with a ruler and a pencil my ray of light coming in and striking that point there. And then using this point and that point, I can now draw the ray of light going through the block. You can see it has bent towards the normal, as we expected. We need to measure two angles here. We need to measure the angle I, the angle of incidence, and R, the angle of refraction. So I place my protractor on here, line it up as carefully as I can, and I can see that by chance it was exactly 25 degrees. And then if we look at this, sometimes it's worthwhile if the line is not long enough, though obviously the ray of light would not continue out like this because it would bend back again. But for the sake of me being able to use my protractor, I've extended it. I can see that it is exactly 17 degrees here. Now, what so the masterstroke of Willebrord-Schnell was Schnell's law, and in a slightly simplified format, but one that you should be able to use, what he proposed was that n, the refractive index of the medium that the light was entering into after passing from air into that material, so this is a material with a refractive index of n, and this is air, or a vacuum, which is essentially the same. And light is travelling across the boundary this way. So n is referring to the refractive index of this new material. That is important. And then what he found, and here is your normal line, and here is your ray of light coming in, and this is how it's refracted down here, the angle of incidence I, and the angle of refraction R, like we just drew on that diagram. Well, what Willebrord decided, or discovered, was that if we take the sine, as in the mathematical function of I, and divide it by the sine of R, then that ratio gives you the refractive index. It's almost like a measure of how bent that line is. If it really bends, if it really changes direction, then n is going to be large. If it doesn't really change direction very much and the two numbers are similar to each other, then it's going to be really small. You see, if it doesn't change direction at all, then this is going to be basically the same number above and below, which will always give 1 when you work it out as a fraction. A refractive index of 1 means it hasn't really done anything, it hasn't changed the angle. So what you can see is that we can use the data that we just collected to work out what the refractive index of our material was. So the incident ray went in at 25 degrees, and the refracted ray came out at 17 degrees. So the refractive index of my material is going to be sine 25 divided by, now you've got to make sure, brackets are a very good thing to do on your calculator here, divided by sine of 17. And so I get 1.44 as my refractive index. It is in fact perspex. And so I was able to work out the refractive index of my material, much less than the refractive index of diamond, and even less than the refractive index of the Philosopher's Stone. But there's one more thing that I want to just point out of how you could use this equation one step further. If you remember the second equation, that refractive index was equal to the speed of light in a vacuum divided by the speed of light in that material, and I know that that same n is going to be equal to sine I over sine R from Schnell's law, then what I can actually do is put C divided by V equal to sine I over sine R. Because if they're both equal to n, then they're going to be equal to each other. And what it means is that from my data, 3 times 10 to the 8 divided by sine I divided by sine R, so sine 25 divided by sine 17, which we know is equal to 1.44, it means that we can work out that the velocity of light moving through our material is 208,333,333 meters per second. Now, if it wasn't genuine perspex, the number would be different from the standard number for perspex. So you can see I can measure the refractive index just by measuring a couple of angles. And it enables me to work out the purity, whether or not it's genuine, what it's actually made of, and this is very important. See, one of the applications of this is to ensure that glass has the properties that you want for it. That if you manufacture some glass to be used in houses, to be used in cars, to be used in glasses, then the glass in all of those substances has to meet very, very tightly controlled tolerances. And so by studying the refractive index of the glass, you can check to see whether or not it is appropriate for the job.